So, welcome back. As you go through this some discussion on unbounded operators and semigroup theory, you realize that many topics have not been covered. So, it is not at all possible because the subject is so vast. So, before stating abstract Cauchy problem, let me just make one remark, because this I said in the beginning. Okay, so this multi-parameter, because this is not very difficult parameter, multi-parameter semigroup, and similarly multi-parameter groups. Okay, so this. So now this T is in Rn plus Rn plus. Okay. So this T is T1, T2, Tn, and each Ti is non-negative. Okay. So same definition. So now multi-parameter semigroup Tt. So same definition, same condition. Okay. So again this is in family in these are bounded linear operators defined on a Banach space. Now it's an Rn plus. Okay. So that's the only difference. So this, since is closed under addition, so we can just take T of T1 plus T2. So now these are n tuples. Okay. T1 plus T2. This is fine. Okay, because this is additive. Rn plus is additive, and same with identity and plus continuity. Okay, same definition. Okay, just so now we can define one parameter sub semigroups. Okay, just pay attention to the notation. So now I am defining only for T non-negative. Okay, it is not an n tuple, just a non-negative real number. So TKT is, so given a multi-parameter semigroup, I can define this TEK. So E1, E2, En are standard basis. Okay. So you can verify if T is a multi-parameter semigroup, then each TKT is a one parameter semigroup. So we get for 1 less than k less than equal to 1. Okay, so we get n one parameter semigroups, and corresponding to each k, so we have generators A1, A2, AK. Okay. So it's like going from one variable calculus to multivariable calculus. So this will be for if we take for example the translation semigroups, then we get all the partial derivatives. Okay. So conversely, so that's why you will not see much discussion on this multi parameter semigroups. So conversely, suppose T1 of course, you can just verify that, and that's going to be the definition also. T of t is T1 T1 Tn Tn. So order is immaterial. Okay, so they all commute. So a multi-parameter semigroup can be written as product of one parameter semigroups, and conversely same thing. Conversely, suppose T1 T2 Tn are one parameter semigroups. Okay. And now you define a multi-parameter semigroup Tt for T in Rn plus by T of T, same thing. Okay, you may assume that they are commutative, mutually commuting, so that the order does not matter. In the first case we can prove that, but in the second case you just assume that. And this is a multi-parameter semigroup. Okay. So you also get this second order derivatives ai, aj, ak. Okay, so these are similar to second order derivatives, the generators similar to second order derivatives. So now you can even define the weak derivatives and other things by taking translation semigroups. Okay, so that's in fact we get also aj. Just these are unbounded operators. You can just check that. Okay, check this carefully. Okay, so equality of mixed second derivatives. Okay, that is similar to that. Okay, but there are some other important things we have not done in semigroup theory, like Trotter-Kato formula and other things. They are important. Okay, but you can read. Those are interested, they can read. Okay. So with that little regression, now we go to this abstract Cauchy problem. In a Banach space. Okay. So first let me consider this first order equation. So du by dt equal to au. Okay, so this is for t positive and some u0 in x. So this is in x. X is a Banach space. So this is our abstract Cauchy problem. Okay. So let me just give the definition. Okay. A function u from, so you can also consider in the whole of R. So if 2x is called a strict solution called a strict solution, strict or strong solution if U is continuously differentiable okay, and ut belongs to dA for t greater than 0 equal to u0 okay, that forces x to be in okay, let me just put t greater than 0 and ACP is satisfied. Okay, that means this, when I take the derivative, that is equal to AU. So, let me come to this initial condition little later. Okay, there is another notion of solution to ACP, and this is called mild solution. So, let me just say that briefly. So, again one more definition. Okay. A continuous, now we are not assuming differentiability. So, u0 u infinity to x is called, so this is like a weak solution, is called a mild solution. Mild solution of ACP, of course, okay, that abstract Cauchy problem. If so, now the condition is not pointwise, but kind of average. If u this t us ds. So, this because of continuity assumption, this integral exists and is a vector in x, and we want this to be in the domain of A for all t greater than or equal to 0 now. Okay. So, because at 0 it is just the 0 vector and the dA is a subspace, and okay, so this u of t is equal to A of 0 t us ds and plus that condition, initial condition x. So, for all t. So, this is obtained by integrating the equation in ACP. Okay. So, this is called mild solution. In fact, it is very important in many applications, especially in control theory. Okay. So, just so here is a proposition for this mild solution. So, let us we are not going to discuss in detail. So, just say that. So, suppose A generates a semi group. A generates a semi group TT and x belongs to x. Okay. So, you define u of t of course it depends on x, so just let me put that way. This is t of t x. Okay. Then u is a mild solution of ACP. Further, mild solution is unique. Mild solution is unique. Okay, so at least we get that uniqueness. Okay. So proof fits already property of the semi group. So just let me so prove only uniqueness is to be proved. So we already know that. So T going to when T is a semi group is continuous. And we also seen that that's how we proved that A is densely defined closure operator. So this integral 0 to t ts x ds is in T. Okay, you put together these conditions, so that prove that U is a mild solution. So only uniqueness need to be proved. Okay, that's okay. So by linearity, we may take x equal to 0. Just you subtract. Otherwise, by linearity, may take x equal to 0, and then we show that any mild solution is 0. Okay. So and let U be a mild solution. Mild solution. Okay. So take T positive, okay, and consider this d by ds of t minus s integral 0 to s. So let me use some other variable here. So u j dj. Okay, so this is 0 less than s less than or equal to t. Okay. So this one you just do this u of s minus t of t minus s, and u is a mild solution. So d by ds of this integral 0 to j, you just see that it's a 0 to s u j dj, and this is same as us. Okay, some work. Okay, so here we are assuming x equal to 0, and you get that 0. So this implies this. Let me write that 0 to t u j dj is 0 for all t bigger than or equal to 0. But again, you use the equation, so that implies, so u of t, because u is a mild solution. Okay, so this 0 to t u j is high and that is 0. Okay, so that proves the uniqueness of mild solution. So we are not going. So if A generates a semi group, then we know how to construct the mild solution. But the converse is we are not going to study here, but converse we are going to study for the strict solution. Okay, so now we is confined to already time strict solutions. I am just going to state a theorem, strict solution. Okay. So let again we will start that T T be a semi group with generator A. So we have already seen that. So if X belongs to dA, then the mapping T going to TTX is differentiable and this is important. So d by dt of TTX is ATTX. Of course, that is also equal to TTAX. Okay, so we already see that. So even for the strict solution, so this implies that for X in dA, if we put U again at Tx as TTX is a strict solution of ACP. Okay. The only thing is we have to take the initial data in domain of A, but not an arbitrary vector in X. Okay. So that's the so converse is also true. Okay. So there are some technical things here. Converse is also true. What does that mean? So if ACP has a strict solution for each X in dA, then A generates a semi group. Okay. So this I will state as a theorem without further discussion. So let me just state that. Okay. Okay. So one more condition. So just I will state E stroke Q. So this is existence and uniqueness. So I am going to state some conditions and the theorem says they are equivalent. So what is this existence and uniqueness condition? Okay. So for every, this is what I was just telling, that every X in dA there exists a strict solution U. Of course, this U it depends on X of ACP and is unique. Okay. So, under this condition we want to prove that A actually generates a semi group. Okay. So, so let me just state as a theorem. Okay. The following statements are equivalent. Are equivalent. Okay. So, there are 4 conditions. So, let me just write that. A generates a semi group. So, again recall that semi group for us means strongly continuous semi groups. So, this we saw as soon as A generates a semi group, we get existence and uniqueness for this ACP, okay, and that is the next condition. So, A satisfies existence and uniqueness, that condition, and rho A is non-empty. Of course, when A generates a semi group, we know that the resolvent set is quite large. Okay, but while proving the converse, you need that assumption. So, this existence and uniqueness plus this condition, and the third condition. So, they are simpler, you see. We do not need the full force of this, for example, this resolvent set. So, A satisfies EU again, existence and uniqueness, and there exists a sequence, of real numbers lambda n increasing to infinity, such that lambda n I minus A. So, this domain of definition is dA. So, it is just restating the this image lambda n I minus A is the whole space X for all n. Okay. And the last one, let me just state that A satisfies EU and okay, dA is dense. dA is dense, and for each sequence, xn in dA, xn converges to 0, we have u. So, that solution UTXN converges to 0 uniformly on compact sets, compact intervals. 0. So, on each compact interval, okay, so this convergence should be uniform as n tends to infinity. Okay. And condition D, Okay, so condition D is referred to as well-posedness. Okay, so from the beginning you are hearing that we are interested only in well-posed problems, so that is existence, uniqueness and continuity with respect to the data. So here the data is this initial condition. So when that initial condition tends to 0, we want the solution also tend to 0, but with some uniformity condition. Okay. So compared to condition B, condition C and condition D are somewhat simpler. Okay. So in applications we want easily verifiable conditions. Okay, that's important. Okay. So I wanted to state a similar theorem for second order equations, but running out of time, so maybe I will do it some other time. Because that we require for the wave equation. So maybe before discussing wave equation, I will just say something about second order equations and then continue with wave equation. Okay, so that with that we come to an end of this brief discussion on unbounded operators and semi-group theory and little bit of abstract Cauchy problem. So from next time onwards we will take up our equations of interest, namely heat equation, wave equation and Schrodinger equation. Thank you.